Good afternoon, everybody. Welcome to the final part of this thermochemistry unit. And actually, this is our last distance learning lesson for the year. Sniff, sniff, I know, I'm sure you're all devastated. But this last lesson is all about chemical reactions and the heat changes associated with that. And we're going to, we've talked about that topic a little bit already. We're just going to put a little bit more of a visual aspect to it. All right, so one of the things that we have already discussed is this little concept right there, that if the change in heat, that's what delta means, change in heat for a reaction is positive, that means we're looking at an endothermic reaction. And by the way, I've had a couple of people ask me this. In earlier lessons in this unit, we had equations like this, and some people said, in those equations, Q is heat. It's in joules. Is there a difference between Q and delta H? And the answer is really no. Both Q and delta H represent energy, okay? Really, the only difference between them is that Q is usually in units of joules, and delta H is usually in units of kilojoules per mole or per gram. But in terms of what you all need to know, they basically represent the same thing. I just wanted to go over that with you. Okay, now, this graph that's in front of you, there's a lot going on here. Okay, this is what's called an energy profile. And let me break this down for you a little bit. All right, right here, I'm going to put a letter R. R stands for reactants. And over here, I'm going to put a letter P for products. Okay, now look at what is on the y-axis, potential energy. If you guys will recall, when we talked about potential energy earlier, we said that is the energy that is stored in the chemical bonds. Okay, so this position right here is representing the energy content stored in the bonds of my reactants. Okay, and this position on the y-axis, if you follow that dashed line across, that is the potential energy stored in the bonds of my products. And I want you to notice that in this particular graph, the products have a greater potential energy than the reactants. And guys, if that is the case, then you're dealing with an endothermic reaction. Let's review what that term even means. Endothermic, heat is required. Heat is absorbed. To go from reactants to products, I have to essentially move uphill in terms of energy. Okay? The reactants have to absorb more energy to get up to the level of the products. Okay? So if you'll notice at the top part of the screen, you'll see the word heat written into the chemical reaction. Endothermic reactions. Heat is absorbed. Heat is treated more like a reactant. Okay? You have to add heat to A and B if you want to get C and D. Okay? So, here's what's going on. Now, we'll talk a little bit more about why the shape is this sort of hill. Why doesn't it just go directly from reactants to products? Okay, but I want to highlight this arrow right here, okay, which is essentially the height on the y-axis to go from my original reactants, right there, up to the top of this hill, okay? The amount of energy to go from reactants to the top of that hill, and we'll talk in a minute about what's going on at the top of the hill, that is called the activation energy. And here's a real simple definition of activation energy. It's the energy required to get a reaction going. Okay, that's a real simple definition. The energy required for reactants to turn into products. Okay. And then if reactants absorb that amount of energy, okay, then it's kind of like, you push the ball up the hill and you get it to right here. And if you get it to the top of the hill, then it can go on and create products. Okay. So again, let me erase that. I don't need that on there anymore. All right, now this arrow right here is the delta H of the reaction. You'll notice, guys, that is the difference just between the level of reactants and products. Okay, so there's two main arrows here. Those are the two that I've highlighted. Those are the two most important on this image here. Okay, the one on the left is the overall change in heat for the whole reaction. The taller one that goes up to the top of the hill, that is called the activation energy. And again, I'll talk in just a minute about what's going on at the top of the hill. Okay, now, if you will notice now, this arrow right here, and I want you to look at this dashed line here. It has the same general shape as the main curve, but it's shorter, okay? And if you look at the line that's describing it, it says activation energy with a catalyst. Now, I can't remember if we have talked about catalysts before, but a catalyst is a substance of some kind that speeds up a reaction, makes it go faster. Okay, now how does it do that? It makes a reaction go faster by lowering its activation energy. Okay, and think about it. Any of you that are runners, okay, if your coach tells you that you're going to be doing some running drills over the top of a hill, okay, if one group is running over a very tall hill and the other group is running over a shorter hill, the group running over the shorter hill is going to reach the finish line faster before the group running up the higher hill. Okay, let's assume everybody's running at the same speed. Okay, so that dashed line is showing you a new curve, okay, but it's this time the reaction is being carried out with a catalyst. It's going to go faster. Now, guys, I want you to notice something on that dashed line is the distance on the y-axis between the products and the reactants. Just that distance. Is that distance different now that we have this dashed line? And the answer is no. Okay, notice this arrow right there, whether you're looking at the solid reaction line or the dashed reaction line, the difference between reactants and products, that doesn't change. The only thing that changes is the activation energy. Okay, so let's look at another graph. Let's look at a graph for an exothermic reaction. Okay, now if you will recall, exothermic means heat is released, okay, produced. And look at our reaction at the top of the slide. Heat is produced, released. You notice the word heat is not on the reactant side like it was before. Now it's on the product side. Okay? Let's label this graph. Okay, we've got, oops, let me undo that. Our reactants are always on the left. Our products are always on the right. Okay. This time, if you will notice, the products, the potential energy of the products, this time is below the potential energy of the reactants. This graph is generally downhill. Downhill graphs are exothermic curves. Okay. Now, we still have an activation energy. Okay. There's still a hill that we have to get over. All right. But it's a shorter hill. Okay. Again, I'll talk about in a minute what's going on at the top of that hill. There's still an activation energy. Okay. But it is generally more downhill. Okay. And again, you could add a catalyst if you wanted to. It would make the activation energy. Activation energy, guys, remember, is the distance from the original reactants to the top of the hill. If you add a catalyst, that hill is simply shorter. Less activation energy, which is going to make the reaction go faster. But look, the overall change in H, the change in heat between reactants and products, that is no different, whether I use a catalyst or I don't. Okay, so you may be asked, if you know that a reaction is endo or exo, you may be asked to draw the general shape of an endothermic curve or an exothermic curve. Okay, endothermic curves, let me just go back one, are generally uphill. Products are higher than reactants. Exothermic curves are generally downhill. Products are lower than reactants. Okay. Something else you might be asked to do is to rewrite a chemical reaction with the change in heat, the energy, as a reactant or a product, depending on which is appropriate. Okay. So if you will look, on this first line, we're given a reaction, and, sorry, I don't want to be using my highlighter. You're given that piece of information, the change in heat for the reaction, and I want you to notice that it is positive. A positive change in energy for our reaction means endothermic. What does endothermic mean? Heat is absorbed. So heat is written in on the reactant side. You can write the actual number if it's given to you, or you can just simply write the word heat. That's fine. Okay, the point is it's written on the reactant side. Whereas look at this other example. The heat value given is negative. That means it's exothermic. Heat is released. Well, how much heat is released? That much. Or if that bothers you to write in the actual number, you can just write in the word heat. That's fine. Again, the point is it's on the product side. Okay. Okay, now let's talk about what is actually physically occurring when a reaction takes place. There is something called the collision model, okay? And that word may seem kind of violent, but chemical reactions are, in fact, sort of violent. Two reactants are not going to create new products unless they crash into each other. They can't just make contact. They have to collide, crash with one another. Okay? However, even that isn't enough. What is required here? they have to crash into each other with a certain amount of energy. That energy is called the activation energy. And that's that vertical arrow we saw on the graphs that goes from the level of my original reactance to the top of the hill. Okay, so there's two parts to the collision model, actually three. But here's the first part. The first key that you need to understand is that for reactants to make new bonds and create new products, they can't just make contact. They have to crash into each other. And how much? They have to crash into each other with a certain amount of energy. That's called the activation energy. Okay? Now, let's say we're dealing with an endothermic reaction. Okay? And I'm just going to make up a number. Let's say that from reactants to the top of the hill is 20 joules. Okay? That means these two particles, these two reactants, must crash into each other with 20 joules of energy. Well, what happens if they crash into each other with only 19? All right? That would be, if you want to visualize it, that would be kind of like pushing a ball almost to the top of the hill and then you stop there. Now, what's going to happen? The ball's just going to roll right back down to where you started. If these two reactants hit each other with 19 joules of energy, nothing's going to happen. They're just going to separate and go back to being reactants again. If these two particles collide with exactly 20 or more, like 21, 22, then I have the chance to create products. Okay? But the point is, I have to meet that 20 joule threshold, and if I don't, then this reaction's not going to happen. Okay, now, they must meet or exceed the activation energy. And what is going on at the top of that hill? What is so special about that? Okay, well, again, here are our reactants on the left. Products are on the right. All right, this thing in the middle right here, EA, that stands for energy of activation. Okay, and notice the pink arrow is the height of the reactants to the top of the hill. Now, what's going on at the top? At the top of the hill, we are forming what's called a transition state. I want you to think of a transition state as sort of like a hybrid between reactants and products. And maybe if you're a visual person, I am, maybe looking at this graph will help you a little bit more. Look at what the reactants look like and look at what the products look like. The transition state in the middle here doesn't look exactly like the reactants, but it doesn't look exactly like the products either. What's happened here is the reactants have collided with the appropriate amount of energy, and new bonds are starting to be formed. Okay, but the process isn't totally complete because I'm not just like my products yet. It's sort of a hybrid. So the energy of activation is really just how much energy does it take to transform my reactants into the transition state. And then once they're in the transition state, then they can go on to create products. Okay? So again, a transition state is sort of like the hybrid between reactants and products. There's new bonds being formed, but I'm not quite to my products yet. Okay? So the collision model talks about reactants have to collide with the appropriate amount of energy. And then there's one other part to it. Okay? Even when things have enough energy and they're colliding appropriately, that's still not a guarantee that I'm going to get products. So what else is required here? Something called the molecular orientation. And guys, that is just a fancy term that means like two reactants contacting each other at the correct angle. Okay? So not only do these particles have to hit each other with the appropriate amount of energy, they also have to collide with one another just at the right angle. They have to hit each other right at the right spot so that new bonds can be formed. If they hit each other with the right amount of energy but at the wrong place where those new bonds can't be formed, then it's not going to work. Okay? So if you think about this, guys, it's honestly kind of a miracle that chemical reactions ever happen because there's so many requirements. They have to hit each other, they have to hit each other with the appropriate amount of energy, and they have to hit each other just at the right spots so that new bonds can form. If we don't meet all of those things, we're not going to get products. Okay? So, that is it. This was a little bit of a shorter lesson. So at this point, guys, you can complete the homework questions and check your answers. And that's it. So this is our last online virtual lesson here. So I hope this has been beneficial for you. I know it's not quite the same as being taught in person, but hopefully we'll be back to that in the fall. Fingers crossed. So anyway, I hope you guys have a great day, and I look forward to seeing you when I see you. All right. Bye-bye.